Welcome everyone to section number 5. This is going to be about curve sketching. But before I get into curve sketching, I got to tell you about one more type of asymptote. And that's going to be here these slant asymptotes. So in this video, right, we wanted to define these slant asymptotes and review some of their properties. We're going to review this polynomial long division, which you may have come across in your favorite algebra class, but we're going to need to use that now. And then we're going to get a little bit of practice finding some of these slant asymptotes. Okay, so first of all, what is a slant asymptote, right? Well, vertical asymptotes are when a graph approaches a vertical line. Horizontal asymptotes are when a graph approaches a horizontal line. So what if your graph approaches a line that isn't vertical or horizontal? And this is the world of slant asymptotes. So in order to get us kind of starting to think about these things, I have a Desmos graph that I'd like us to go ahead and play with and try to find the slant asymptote of 2x squared minus x over x plus 1. So I already have it loaded here, but you may also want to load it. And you can see, okay, here's our graph, 2x squared minus x over x plus 1. So it has a vertical asymptote at x equals -1, right? Because that would make you divide by 0 here. So we can see, yes, vertical asymptote. Now, as you zoom out, you'll notice that this graph, it seems to get closer and closer to this straight line, right? It looks very similar to this straight line right here. And the question is, what is that straight line? Because that's our slant asymptote. That's what slant asymptotes look like. It says as you go towards infinity or negative infinity, it seems to get closer and closer to a straight line. But that straight line isn't vertical or horizontal. Okay, so in this case, we're just going to go ahead and play with this thing and see if we can figure out what that straight line is. Okay, so I have this now blue line that we want to try to match up as best as possible. So maybe first of all, let's play with the slope a little bit here and try to get a slope that matches. Actually, I think that looks pretty good right there. Right, okay, so a slope of 2 seems to do a pretty good job. And now let's go ahead and change the height a little bit. That seems all right. -3.2. Yeah, and it seems as you get farther and farther out, it seems to get closer and closer to this blue line. They do seem to be right on top of each other. What happens if I change this to -3? I'm just thinking it's kind of weird for my answer to be -3.2. So -3 also looks good, but this is saying that maybe from this picture, it's hard to tell, right? As you kind of zoom out, either -3 or -3.2, they both look pretty good. Okay, so which is it, right? And that's where we need to use our good old friend, this polynomial long division will come in and help us be able to solve and figure out exactly what it is. But right now we're thinking 2x minus 3 looks pretty good. All right. So now that we can visualize these things, I guess let me go ahead and write down here, we think y equals 2x minus 3 looks pretty good. And I'll go ahead and put a question mark here because, right, we also looked at y equals 2x minus 3.2, and that looked fairly reasonable as well. And so we want to know, okay, based on the graph, it's maybe hard to tell what is it exactly. Okay, so we need a more formal definition here, and here is the actual definition for slant asymptotes, right? Okay, so we have a function y equals f of x has a slant asymptote, and that's sum y equals mx plus b if, as x goes to infinity, if you have your f of x and you were to subtract away that line, so subtract away that mx plus b, that this then would go to 0, right? That their difference would be 0 as x gets very, very large. Or if the limit as x goes towards negative infinity, if you were to take this function and subtract away the line mx plus b, their difference would go to 0. Here, maybe I'll go ahead and do some brackets around here to really show that you're taking the limit of both of these things. So this is the formal definition of a slant asymptote. All right, but on homework, quizzes, exams, right, this kind of Desmos thing was very nice, but we don't get a calculator or computer, so how are we supposed to find slant asymptotes? And as I kind of mentioned before, the answer is polynomial long division. So we need to use polynomial long division to find these slant asymptotes. So it's possible that you may have never come across polynomial long division, or maybe you did a long time ago. So I want to do a little bit of a review on how do we do polynomial long division in this class. So I want to actually stop and kind of move backwards one more step and do just regular long division, because the claim is, well, there are some similarities, and if you're happy with one, then the claim is we can get happy with the other. All right, so we have 219, and we're going to go ahead and divide this by 12. So 219, that's the numerator, divide it by 12, and if you remember this from back in maybe your elementary school days or something like this, right, you asked, what do you multiply by 12 to get 2? And the claim is, well, 12 is bigger than 2, so it'd have to be a fraction. So, okay, let's go ahead and move over. And you say, what do you multiply by 12 to get 21? And you say, well, nothing does it exactly, but okay, so what's the biggest thing that I can multiply by 12 and get close to 21, but not over? And the claim is 1 is as good as you can get. So 1 times 12 is 12, and then you went ahead and subtracted these, and you got 9. Then you go ahead and you bring down this last digit, the 9, and you ask, what do I multiply by 12 to get as close to 99 as possible? Even equal to 99 is great, but not going over. So again, as close to 99 as possible, but not going over, and I claim that the answer is 8. So if I multiply 8 by 12, let's see, so 8 times 2 is going to be 16, and then 8 times 1 would be 8. Plus that extra 1, so that's going to be 9. So 96 altogether if you do 8 times 12. And you go ahead and subtract this, and you get a remainder of 3. So we can go ahead and express 219 twelfths as the quotient, which is 18, our answer here, plus 3 twelfths. So the quotient plus 3 twelfths, so that's the remainder here. So let me go ahead and just remind us, this is the quotient. And this right here, this 3 is the remainder. And so we can verify that this is true, but again, the main thing that I want to get out of this problem is this technique right here. Okay, so let's go ahead and play the same game, but with polynomials, right? So I have 2x squared minus x, and I'd like to divide that by x plus 1. Now polynomials are a little bit different, right, because they have these extra terms, right? So it's x plus 1. It's just not one thing over here. But you ask yourself very similar questions. What do I multiply by x in order to get 2x squared? So you only really consider these leading things. What do I multiply by x in order to get 2x squared? And here the answer is 2x. So if you go ahead and you do that and you multiply the 2x by x, you indeed get 2x squared, but you also have to multiply by this 1. So 2x times 1 is going to be plus 2x. And now you go ahead and you subtract it all. Just like before, we subtracted whatever this result was. And so 2x squared minus 2x squared, that's 0. It's great, we're actually getting somewhere. And then you have negative x minus 2x. So that's going to be negative 3x. And now you play the same game. What do you multiply by x in order to get negative 3x? Well, that's going to be negative 3. So we have negative 3 times x plus 1. So negative 3 times x is negative 3x. Negative 3 times plus 1 will be negative 3. And now we go ahead and we subtract this. So we have negative 3x minus a negative 3x. So that's going to be plus 3x. That's going to be 0. And we have nothing here. If you'd like to, you can even imagine that there really is a plus 0 here, and you brought this down. But 0 minus negative 3, so that's going to be plus 3. And that's the remainder right there. So the remainder is 3. If you wanted to know what do you multiply by x in order to get 3, well, you'd have to use like a reciprocal function or something like this. It would be very messy. It's not a polynomial anymore. Okay, so this is where we stop, and this suggests that we can write 2x squared minus x over x plus 1 as the quotient 2x minus 3 plus the remainder 3 over x plus 1. So this is the same form that we had before, right? We have the quotient, and then we have the remainder, whatever that is, divided by, well, the same thing that we were dividing by up here, right? That's the divisor or the denominator, right? All right, so it looks very similar, but maybe the first time we do this, well, we should be a little bit skeptical, right, that this actually works out. So let's go ahead and do a quick check here, and I'm going to work our way backwards with our answer here and see that we can get what we started with. So if I wanted to go ahead and combine these, well, let's get a common denominator. So I already have the 3 over x plus 1. And then let's take this 2x minus 3 and let's multiply it by x plus 1 in both the numerator and the denominator. So that would give me a common denominator here. Well, here we would have 3. We have our common denominator, x plus 1, but we need to go ahead and FOIL this out. So let's see what we would get. So the 2x times the x would be 2x squared. The 2x times 1 would be plus 2x. Negative 3 times x would be negative 3x, and negative 3 times 1 would be negative 3. And so we can see this plus 3 here and this minus 3 here would go ahead and cancel a little bit. And let's see, we have 2x squared, and then we have 2x minus 3x. So that's going to be negative x altogether over x plus 1. And so now we can see that this is actually the same as what we started with over here. And so this is just a different way to represent the same thing. Okay, so we didn't mess up, right? We did a good job. So we were able to actually do polynomial long division on this thing. And I told you that this was going to be the answer, right? And so the claim is here, use the definition of the slant asymptotes to verify that our quotient from our answer in 5.4, that's this one right up here, is the slant asymptote. So again, remember our quotient was this 2x minus 3, and actually that was one of the things that we thought was the slant asymptote, right? 2x minus 3, we thought this was the slant asymptote. Let's go ahead and verify. So for slant asymptotes, you do the limit as x goes to infinity or negative infinity of our f of x minus this mx plus b, this line that we think is the slant asymptote. So in this case, we're going to do the limit as x goes to infinity. Our function is this one up here, this 2x squared minus x, 2x squared minus x over x plus 1. And we're going to subtract away this quotient, so this 2x minus 3. Now remember, we learned another way to represent this 2x squared minus x over x plus 1. By our polynomial long division. So we're going to go ahead and switch that out and do the limit as x goes to infinity of 2x minus 3 plus 3 over x plus 1. And that again is a different way to represent this 2x squared minus x over x plus 1. And now we need to subtract away what we think is the slant asymptote. So in this case, 2x minus 3. And when we do that, you can see this 2x minus 3, and then you subtract away 2x minus 3. Those perfectly cancel out. And so we're left with the limit as x goes to infinity of 3 over x plus 1. And now we're in really a horizontal asymptote style question, right? The degree of the numerator is 0, the degree of the denominator is 1, and so therefore as x goes to infinity, this is going to go to 0. Which is exactly the definition for the slant asymptote, right? If this thing goes to 0, then whatever this y equals mx plus b is, that is a slant asymptote. So therefore, in this case, y equals 2x minus 3 is a slant asymptote. And now you may be asking yourself, why did we go to positive infinity and not negative infinity? Well, we can also consider that case, right? So if x is going to negative infinity, the claim is pretty much all of these same steps are the same, right? So nothing really changes, but then here at the very end, you're going towards negative infinity. And again, your degree of your numerator is 0, your degree of your denominator is 1, and therefore this will still go to 0. So kind of in either direction, either going to positive infinity or negative infinity, this will end up going towards 0. And that's something that we saw back in our graph here, right? Kind of the difference between these things, as you go towards either negative infinity or positive infinity, they get very, very close to each other. So again, the difference will be 0. Okay, let's go ahead and formalize this a bit more with this remark. which says after simplifying a rational function using polynomial long division, if the quotient is a linear function, then it is, and as you would probably suspect, it is the slant asymptote. All right, let's go ahead and try one more example. I would recommend pausing the video, trying to get as far as you can on this, then go ahead and unpause it and I'll spoil the surprise. Okay, so again, we're going to want to use, well, polynomial long division. So x squared plus 3x plus 2, we're going to be dividing that by x minus 2. What do I multiply by x in order to get x squared? Well, that's going to be x. Double check, x times x will be x squared, x times negative 2 will be negative 2x. We go ahead and we subtract that away. So x squared minus x squared, that gives us the 0, great. And we have 3x minus negative 2x. So that becomes plus 5x, and then we go ahead and we bring this 2 down. Next question, what do we multiply by x in order to get 5x? Well, that's got to be 5. So 5 times x will be 5x. 5 times negative 2 will be negative 10. And remember, we're subtracting this away. 5x minus 5x, that'll be 0. And then 2 minus negative 10, so that's going to be 2 plus 10, that's going to be 12. And if you were to ask yourself, what do I multiply by x in order to get 12? Remember, that's not going to be a polynomial, so that's where we stop. And so based on the remark that we have up here, right, the quotient, well, this is a linear function, right? And therefore the quotient here, this x plus 5, this is going to be the slant asymptote. Now, if you want to go ahead and check, maybe you're paranoid that we made a mistake or something like this, I don't blame you. But it's useful to go ahead and recall that we can now represent this as the quotient, x plus 5, plus the remainder, 12, over the divisor, x minus 2, or the denominator there. So using the polynomial long division, this is another way that we can represent this. And so if you wanted to calculate out the limit as x goes to maybe infinity, for instance, of our function, x squared plus 3x plus 2 over x minus 2, minus the thing that we think is an answer, so in this case, x plus 5. Well, we'll have the limit as x goes to infinity, and it's useful to go ahead and switch this out now for the x plus 5 plus 12 over x minus 2. Subtract away x plus 5, and so now you can see that we're going to get some nice cancellation here. And we're going to be left with the limit as x goes to infinity of 12 over x minus 2, and we have a degree 0 over a degree 1, and therefore this limit is going to go towards, this limit's going to go towards 0, right? You can imagine as you're plugging in bigger and bigger values, maybe you're plugging in a million or a billion or a trillion for x, right? You have 12 divided by, a million minus 2, a billion minus 2, a trillion minus 2. Imagine if you have 12 pizzas and you have to share them with a billion people. How much pizza is everyone getting? Well, basically 0 pizzas, right? This is getting very, very close to 0. And so again, this was all some check right here. And as we do more and more of these problems, you'll be confident, right, with your polynomial long division, and you'll be able to stop right here and see that y equals x plus 5 is the slant asymptote. All right, guys, that's it for this video. I'll see you next time when we actually do a few curve sketching problems. We're going to smash kind of all of the sections that we've done more or less in chapter 3 up until now together into these giant problems. So we'll only do a few of them, but that's the heart of curve sketching. I'll see you then.